breathing system classically has been described as, who else is waiting? I like Nadira to came in ready. I think Nadira's line got problem lah. She in? Okay, she's in. Good. Okay. So classification breathing system can be divided into two types of classification. One based on whether it's open, semi-open, semi-closed or closed. That has been described by these two guys, Collins and Briggs. Another type is based on whether that system has a CO2 absorption, which is your Coda line for scavenging, or without the CO2 absorption. This is by the guy called Conway. So first, you have to know this type of classification. The notes or whatever pictures I've taken all as the information in podcast. Please, after this lecture, I hope you all have read it before. If not, after my class today, please go and have another session of reading so at least you'll understand better. So the type of open is air and agent, exhalation into atmosphere. There is no reservoir, there is no rebreathing. This is just an open breathing, either using a T-piece or nasal prong. We don't use this very openly except for nasal prong, but in nasal prong, there is no agent. The agent can be oxygen, okay? Air plus oxygen. So that's nasal prong, which is open. There is no connection. It's open to atmosphere. Open means it's open to atmosphere. Semi-open, it's partially closed. So it means there is a reservoir, a small reservoir, and small breathing. Like either T-piece with small reservoir, your high flow mask. So all these as a small reservoir. Air plus agent from machine, atmosphere. You exhale to atmosphere. There is a small reservoir, the high flow mask. There is small rebreathing. You rebreathe from your high flow mask if the high flow mask doesn't have an exhalation wall. If there is exhalation wall, it doesn't rebreathe. Semi-closed is what we interested. Semi-closed and closed. These two are hardly in practice in anesthesia. Okay, in anesthesia because you can't give any agent, inhalational agent in open and semi-open method. In semi-closed, inhalational agent is from the machine, and inhalation oxygen, everything is from the machine. Exhalation is atmosphere and machine. Okay, semi-closed. Your scavenging system can be open to atmosphere or can be going into a scavenging part in your machine. Reservoir is large, means your whole circuit system is your reservoir. Rebreathing is possible. This is your Mapleson system or vagal attachment. We go to, so your Mapleson system in your MCQ, you must know your Mapleson system comes under semi-closed type. Okay, and then closed is the circle breathing system that we use in our machine, GA machine. You inhale from machine, either oxygen, air, nitrous, or gas, everything from that inhalation agent, and you exhale to machine. You never let to atmosphere because it can cause atmospheric pollution and also cause harm to the other personnel in the operation theater. The reservoir is large again. Rebreathing, yes, plus CO2 absorbent. Okay, you rebreathe from your exhale thing that goes into your inspiratory limb again. I will talk to about in the diagram later. And also you have a CO2 absorption, your soda line. So your circle system is a closed system. Your Mapleson system is your semi-closed. Your T-piece is open. Okay, either T-piece with the reservoir. If you see in children, some T-piece doesn't come with the bag. Some T-piece has a bag. We attach a bag. Currently, all the T-piece we have a small reservoir bag. The bag that we inflate and deflate. Okay, manually. Next is Conway classification. Conway classify it with CO2 absorption or without CO2 absorption. With CO2 absorption, as I mentioned, unidirectional flow is the one that we are using, circle system. You inspire the patient, the inspiratory breath goes to the patient in one limb, and the expiratory breath comes in another limb and goes to scavenging, and that's the curve. Okay, there is a carbon dioxide absorption system, which is your soda line and scavenging. Bidirectional to and fro system using one limb, the same limb to inspire and expire using an exhalation and inspiration valve, which can cause a lot of patient desynchrony. Currently, it's not commonly used or very famously used. Then without the CO2 absorption, you have unidirectional flow, non-rebreathing system, bidirectional flow. You have Mapleson A, B, C, and everything. All these are not so important, but you have to know there are two different types of classification. Okay. Next, so the most important part of this class is your identifying Mapleson system. I don't think anyone here can easily, if I give you a system to you, can you identify the system whether Mapleson A, B, C, D, E, or F? It's quite difficult. None of us can remember. So you have to come up with a mnemonic, or you have to come up with a system on your own for you to remember this better. I watched few videos when I was studying for finals or primary or MCI. I watched few videos, few website and everything. I've come up with one of the website or video explain this very easily, and I think that's the best way to remember this. Okay, you don't have to know this system in reality because we hardly use this now. It's all for exam purpose. So you have 6 different classification of Mapleson, A to F. Okay, so how do we gonna remember this? Which is which component is missing in which, and which component is added? So you have to know there are 4 main components in each Mapleson breathing system, which sometimes can be there, sometimes not there. By presence or absence of one of these components, you can identify which is which. Okay, first, fresh gas flow. Fresh gas inlet, it means the oxygen is going through a new oxygen is going through this inlet. Okay, there is a fresh gas flow. Whether the system has a fresh gas flow or not, and where is the fresh gas flow is situated, which part of the system. Is it near to the patient or away from the patient? So that is one important thing to say. Okay, next, APL valve, adjusting pressure limiting valve, right? Where is this situated? Is it situated near to the patient or away from the patient? And is it present or not present? Fresh gas inlet must be present in all the systems because you need oxygen, but you want to know where is it situated, near or away from the patient. APL valve might or might not be there. And if it's there, is it near to the patient or away from the patient? Third, your reservoir bag. Your reservoir bag. Does the system has a reservoir bag or does not have a reservoir bag? So you have to know that part as well. Fourth, corrugated tube. This part, this breathing tube, the corrugated tubing we use, does it present or does not present? Whether is it there or it's not there? The corrugated tube is the one that connects the fresh gas inlet to the patient. So is it present or is not present? So if you see it there in this one, I haven't talked about which Mapleson. Now I'm talking about generally Mapleson system. So you have a fresh gas inlet, your corrugated tubing, your bag, and then your valve here, and then your patient end. Okay. In this picture is important for you to know because usually our corrugated tubing are 1.6 meter. This one can come in MCQ unless you're extending it on your own. And then our bag usually is 2 liter, the capacity, and the end that connects to the patient gas is 22 francs, and then the end that connects to the patient is 15 francs or 22 meter. All these can come out in MCQ. Okay, next. So how do we gonna define which differentiate which is which? Follow me as my going. Anyone have a problem, ask me directly now so I can repeat it. This is how you're gonna remember it. Once you know how to remember it, you will never forget it. Okay. First, Mapleson A. A, you remember APL. The APL is on adjusted pressure limiting valve is on the patient side. Only the APL is on the patient side. Everything else is away from the patient. This is the patient. Only your APL valve is near the patient. Corrugated tube is after that. Fresh gas flow is after that, and reservoir is after that. Only APL is near. So Mapleson A, only APL. A for APL is near to the patient. That's how you identify. None other system as. If you compare with B, next we go to B. B is for both both APL and fresh gas flow is near to the patient. Only in Mapleson B you will find this fresh gas flow and APL. Only in Mapleson A you will find APL alone is near to the patient. Okay. In Mapleson B, it's a full system. It contains all four. It has a corrugated tube. It has a fresh gas flow. It has APL. It has a reservoir. But the fresh gas flow and APL are near to the system. Okay, that's the difference. So both APL and fresh gas flow near to the system. So A and B are complete system. In the complete system, APL is near to the patient. B, both fresh gas flow and APL near to the patient. Next, we go to C. C, no corrugated tube. It's an incomplete system. It has a fresh gas flow, it has APL, it has a bag, reservoir bag, but it does not have corrugation. C for corrugation. It does not have corrugation. Okay. Next, D, distant APL. The APL is, this is a complete system again, but the APL is away. If you see in all the system, only in D, the APL is distant, away from the patient. Okay. Next, in E is for empty. What it means empty? It only have a tubing and fresh gas flow, but it does not have a valve and bag. No bag, no valve. It is empty at the end. It's empty in the other end. This is the only system which does not have a bag. No reservoir bag and APL valve. Okay, both are not present. And F is flux mean valve, right? What's the meaning of flux? Flux means influx or efflux. Either is letting in or letting it out, or control the movement of the flow, right? So valve is the function of the valve, regulates the flow, whether it's letting in or so. I remember it as F is for no flux, no valve. This system has everything else except there is a no valve. So no flux, no valve. So this is the easiest way I can remember it. So I don't know whether it works for you all or not. You all want me to repeat? I'll wait for 10 seconds. If anyone wants me to repeat, please tell me now. I will repeat it now. This is very important. This will comes out in MCQ. Very famous. Mapleson system is very famous and it will come out in MCQ. So you have to know this by heart. Okay, there is no one asking me to repeat, so I'll move on. So this is just the repetition. So you see in Mapleson A, the pressure limiting valve is near to the patient. Okay. APL is on patient side. So the fresh gas flow comes in, this is the reservoir bag and it goes to the patient. Patient exhale, the APL valve will open, your exhale breath will go in here. So there is very limited rebreathing because the exhale breath goes out here, fresh gas flow comes in. So there is limited rebreathing. In B, if you see, B has two different types. One has only single limb, right? Inside the limb, there is a lag modification of a Mapleson system. Okay, B is actually a lag modification of a Mapleson system in which you see, Mapleson A got two types, either McGill or lag. Okay, there are two versions. It's a modified system of McGill. They come out with lag where they kept the pressure limiting valve at the end. So that's a different thing. So you know, just remember that if you put the pressure limiting valve at the end, that's called lag. But you don't have to remember that by heart lah. No need to worry about that. Why Mapleson D system is no more? Because it's obsolete. We don't use it nowadays. Then you have a Mapleson D system. All these are just repetition. You all can read in podcast about this vein coaxial ISPPs. Mapleson system is called as ISPPs. CPs earlier part is empty, right? Does not have a bag and the valve. Currently, we added on a valve. So this is called Jackson modification of ASPPs. So all this you all read can podcast lah. Okay. don't waste time. So again, this is again about the you have to know how much of minute ventilation is needed. If all these are, as I mentioned, are semi-closed, so there will be some leak of air. So increased fresh gas flow is needed. So most of it from B to F, all will need 2 to 3 times of minute ventilation. You have to give extra gas flow. Okay, you really have to give extra gas flow. Except A. A is very good, is very give you little leak. So that's why you can give equal to minute ventilation, very high and difficult to predict. So it's like very good. So how you want to remember this? Which one is good for spontaneous breathing? Which one is not good for spontaneous breathing? Or which is the best efficient one for spontaneous, best efficient for control? Again, mnemonic, the best to least efficient. For spontaneous breathing in all the system, the A is the best system for spontaneous breathing. You see, equal to minute ventilation means very little leak, and followed by D, C, and B lah. B will be the least efficient for spontaneous breathing. In controlled breathing, Mapleson D is the best, followed by B, C, A. So all dogs can bite, and control that bodies can't argue lah. This is how I remember. So all this, I'm giving you the tips, whether you want to take it or you want to make your own mnemonics, up to you. So if you look at it, D in control, if you look at A is best for spontaneous, equal to minute ventilation. But in control, it needs a very high minute ventilation. It's not good. But D in spontaneous, it increased gas flow. It needs a higher minute ventilation. But in control, it just needs almost 1 to 2 only. Okay, most efficient for controlled ventilation is D. Most efficient for spontaneous ventilation is A. So remember that. So this is my notes, which I scribbled, and almost every information is here. What all I mentioned about the mnemonic and everything, I just leave it here. It's quite messy, but most of the informations are there, so you all can have a look at it. Why the Mapleson E is the ISTPs is mostly used in pediatric group is it can use up to below 30 kilo of the patient, not up to, it can be used in patients below 30 kilo. Why? Because ISTPs, as I mentioned, it does not have a valve. So when there is no valve, there is less resistance to breathing. Pediatric cannot cope with high resistance for breathing. So there is no valve. So that is the best part for pediatric use. So ISTPs, exhalation tubing provide a larger volume and tighter volume to prevent increased resistance to breathing. So that's why we use in patients who have extubated. We just use that ISTPs while we are sending to recovery, and then we extubate them because it's less. So, but it does not have a reservoir. That's why Jackson Reese modified the ASTPs by adding a reservoir bag there. There is an APL valve in the reservoir bag, which is we manually control. In the pediatric ASTPs, which is the reservoir, you see the bag as a hole at the end, like a tail with a hole. The hole we will use with our finger to control at the APL valve. Will open and close. If you all have done peach case and use the ISTPs to transport patients, you should use it. But so far in HSA, I've never used it. I don't see them using it. So Mapleson E with the breathing bag connected to the end of the breathing tube to allow controlled ventilation scavenging, commonly used for pediatric patients and transportation. So that's about it. So we go to circle system. Circle system is a full, complete, closed system. There is no leak or very minimal leak. Okay. So it has a patient end and a machine end. So we start from the machine end, where is the fresh gas flow comes in. The fresh gas flow will comes in from the machine here. Will go to the inspiratory unidirectional valve. If you all see in the ventilator, before the circuit, the tubing comes out, there will be two valves that goes up and down all the time, like a circle thing with the star there, it come and up and down. So that follows your inspiration and expiration. So when the fresh gas flow comes in, the inspiratory valve will open, and the fresh gas flow will go into the inspiratory limb, our wide tubing inspiratory limb, and goes to the patient. And when patient exhale, the exhale breath will go into the expiratory limb, and moment the patient is exhaling part of that, during that part, the inspiratory valve will close and expiratory valve will open. So the expired gas will comes over here, will go to the reservoir bag or scavenging, and then goes to the soda lime. And then once it already has been filtered with the CO2, it will join the fresh gas flow to go again to the patient. This is the full circuit system. Okay, how the reservoir and APL valve works is based on our whether we are switching on the ventilator. This circuit system is devoid of the ventilator part, which is connected here. So I'm not including it. I'm only talking about the circuit system. How the ventilator controls this, and when we switch from ventilator to manual, how we use this, we'll talk about it later. So again, you look at it. First, number one, fresh gas enters the circle from the common gas outlet of the anesthetic machine. Goes, flows through the inspiratory limb one-way valve, then flows through the inspiratory breathing tube, through the white piece to the patient. The patient exhale, number 5, from the patient through the expiratory breathing tube, goes to the expiratory limb. Expiratory one-way limb valve will open, and this will go to the number 7, in and out of the reservoir bag. If the patient is not manually breathing, it's a controlled breathing, right? If you can see some Drager ventilator, the Datex Omeda, it doesn't allow the bellow to go up and down while manual, but in some spontaneous also moves in. So like this in a patient, if you see, if the patient is on a controlled breathing, when you put on a ventilator, the reservoir bag does not have a function. Only the bellows moves in and out lah. So if the patient is breathing himself, the gas will go to the reservoir, but it comes out. Excess gas will goes out through the APL valve to the atmosphere and scavenging. Next, the excess gas will comes in the reservoir, will come out and goes to the CO2 absorption system, soda lime, the absorbent canister where the excess CO2 is removed, and then the filtered air will go through the limb to join the fresh gas flow. Why is it important? So minimize the requirement of the fresh gas flow. Rebreathing system is available, but the rebreathing is without the CO2. The CO2 has been absorbed. Okay, this is just a repetition. You all can go through this again on your own. You start from the inspiration, the fresh gas flow goes in and then follow, and then you follow this also after that. Okay, so again, this is my own notes. I have simplified it. I put step by step. I made a very simplified schematic diagram on my own. This is for my own understanding. You all can go through this. I've mentioned here during inspiration. So this is a circle system, again, without the ventilator involved. Okay. Then on spontaneous breathing, when you manual back, what happened? And after that, when you put the patient on IPPV, patient is not breathing, you paralyze the patient. So what happens? This is the ventilator part. How ventilator actually control the gas flow. Then you put that ventilator things inside here. During inspiration, what happened, and expiration, what happened. I'm not going to go in detail for your level. This is actually for finance level. But since I'm talking about breathing system, I give it in here. You all can go through. One of the days when we are in OT, I can actually show this. This have to be explained with the GA machine in place. So you all don't get confused. You can't simply explain this. Okay, next we go to HME. 5 minutes. Then we stop it. Then we go to the next topic. HME is heat and moisture exchanger. So this is the HME. When you see HME alone, this is the HME. HME is can be with filter or without filter. If you can see, there are part in the near the ventilator end. We will connect this near the ventilator end. This is just a filter. This is not HME, even though we generally just call it HME. This is just a filter because at the machine end, the machine doesn't need a HME. It doesn't need a heat and moisture exchanger. It does need a filter alone. Filter from the patient's viral load or bacterial load, whatever organism, and also from the debris or secretion. It's just a filter. Okay, but at the patient end, you need the HME. So at the patient end, the HME can be with filter or without filter. So HME usually now all comes with filter because we want to prevent the further circuit being contaminated. So HMEF, we call it HMEF. HE, the moisture exchanger with filter, electrostatic filter. So it can be in multiple types, in circular motion or pleated filter with HME property. Remember, there is only one filter which we put in the machine end. Patient end, we usually put HME with filter, even though we generally call it. Okay. So there are many different types of it. You have a blue, green, yellow, and everything. But generally, even though this is not a universal rule, but books mention that if HME only, okay, if HME only, it will be blue. If filtration only, it will be yellow. HME plus filtration is green. That one we usually use lah. Okay, in our ICU setting, everything we use a green HMEF. So which has HME plus filtration. Filtration only is yellow, which used at the patient side. Sorry, filtration only. HME only is blue. You might have seen in some places, there are only HME only, a blue color thing. Okay, I think I have a picture of it. So what is important, you must know the filter is hydrophobic, means better for fluid and particular contact. It means it expels the water. It filters the bacteria, virus, and latex particle when passive humidification using an HME is used. The circuit is termed a dry circuit, as opposed to a wet circuit using active humidification. Active humidification is your ventilator machine, or you use a high flow nasal cannula. We have a humidified water bath, which is not good. That's why patient will always complain the water is going. It's active humidification that got patient discomfort. Okay, that is a wet circuit. If you use an high flow nasal cannula, you want to fix the water bath. When you use HME alone, it's a dry circuit. Uses humidification, warming inspired gases, and microbiological filtration. Best used in patients with few secretion who are not hypothermic, do not have large air leaks, and do not have high airway resistance. Because if a patient has very large secretion, you have to change multiple times. That's one, and it increases the resistance. And the patient is hypothermic, the HME will always conserve the heat some more. The patient become more hypothermic and do not have large air leaks and do not have high airway resistance, because HME increase the airway resistance of the circle system. Description contains a layer of foam of paper embedded in hydroscopic salt. Do you remember hydroscopic salt, which acts as such as a calcium chloride? It's hydrophobic filter, hydroscopic salt, bacterial and viral filter, filtering efficiency of 99.9%, very important. HME with humidification efficiency of 30 milligram per water liter. This one also connects to a standard 15 mm connector on an endotracheal tube. This is also important, the 15 mm. So all this you all can go through on your own, the components of it. Okay, the connect standard 15 mm or 25 mm attached to the ventilator circuit, and 15 mm connect to the patient's airway. Okay, just go through it on your own. Again, mechanism of filtration. Filtration is achieved for larger particle, 0.3 micrometer, by initial impaction and interception. Impaction and interception for larger particle. Small particles less than 0.3 are by Brownian diffusion. All these extra information are given, all these for finals, not for your level. You have to know the efficiency is 99.99%. Resistance can be up to, this not important. The part of this humidification efficiency is important. Okay, how do they work? So you see this the machine side, this the patient side. The humidification, you see, from 30% when goes to the patient is 100%, but the heat comes down to the machine side. From the patient, from 37 degrees Celsius, it conserves the heat here and goes to the patient side. So when the fresh gas flow goes back, the heat is being given to the patient. So patient does not lose heat. But in humidification purpose, patient here is the gas that comes from machine is very dry. But once it passes through the HME, it moisturizes the gas. So the gas will go to the patient. So patient does not inhale a very dry air. The dry air that patient get is dry and heat, has some heat. So patient does not go hypothermic. Okay. Main advantages: easy to use in breathe-in circle, cheap and disposable, 60 to 70% relative humidity achieved. This is very important. Temperature achieved range from 29 to 34, can be incorporated as a microbial filter. Benefits again, go through on your own. All this can go through on your own for MCQs. This is for COVID per se. What is important? COVID-19 coronavirus is 0.05 to 0.1 micron. Okay. But our filtration efficiency, just now I mentioned, it can top up to, sorry, where was it? Less than 0.3 microns are captured by Brownian efficient. So COVID-19 particle might not be a good thing that can be captured by this HME alone lah. Okay, it might work, but they say there's possibility it might not work lah. Okay. Then how to insert, where to insert, you must know this, where to insert, do not insert. So you must insert near to the patient. Okay. So this is your patient ETT, is always closer to the ETT, not away. So patient and the ETT, your HME, then only your Y limb comes in. If you got to put in a nebulizer, put a nebulizer near to the patient. After that only you put HME. You put a nebulizer after the HME, none of your medication going to pass through the HME to go to the patient. Okay, that's about it.